Hello, I'm Nicholas Taubert, and this is my algorithm analysis of a Magic the Gathering aggro simulator. To start, for those of you who don't know how Magic the Gathering works or how to play, that's okay. This is a pretty simplified simulator meant to test the effectiveness of a certain kind of deck. It is a common trope for red creatures to cost X mana to cast an XX with haste. This just means you have to have one land in play for each symbol or little gray number, and they deal 1 damage per turn per mana they costed, and can deal that damage the turn they come into play. Once you do 20 damage total, you win. You can only play one land a turn, but they stay in play and help pay for a creature once per turn. This simulator takes a deck input in the form of a vector of integers, then with lands represented as a -1, and the rest are an integer value that matches their non-negative mana cost and attack damage. So, like in this case, Raging Goblin would be a 1 because he's 1 for 1/1, or Lava Hounds would be 4 because they're 4 mana for a 4/4. So they deal 4 damage. That's all you really have to know for this. Um, so here's what the actual program looks like, just to give a better idea. And I have a couple different decks already loaded into it. Um, so a good test one is this one. This is a very obscure situation where I purposely loaded a deck in order of descending mana cost, meaning all the lands don't come out until the end, so you can see how it works. It tries to play a land every turn, then plays all the creatures it can as effectively as it can, then attacks with them all, and the program returns how many turns it takes to win, or a -1 if you never win, which is very rare. When you end a turn, if you have more than 7 cards in your hand, you have to discard them until you only have 7 in your hand. Uh, so that's why it stays at that number the whole time. Additionally, the program discards the highest mana cost card because it knows it doesn't have enough mana to cast the others, so it will prioritize saving cards that cost less. You can kind of see that up here, especially. Um, a much more realistic, honest, random example would be this one, which is just the previous deck but shuffled or randomized in a way. And you can see kind of how the program runs and how a game would kind of go. So you can see if this were your hand, your expected turn would be to play one land and then play the creature because he costs 1. Now, in situations like this, there's a very important decision-making process. We want to maximize the damage done every turn by playing the combination that utilizes the most lands and therefore outputs the most damage per turn. Therefore, the program must know to prioritize a 2 and a 3 over a 4 if only 5 mana is available. Because if the 4 was chosen, then the damage would only be 4 that turn, whereas it could have been 5. Here's all the code. If you'd like to pause and get more specifics on how it all works, since I'm limited on time, I'm going to move on from here. And I'll explain the important parts in a little more detail. I'll have enough time to explain all the aspects of the function, of the entire simulation function, but all that really matters about them is that they mostly have negligible runtime, so it'll all be inevitably consumed by the ceaseless hunger of the complexity of play spells. The most interesting part of this program, for where this workshop is concerned, is this blue function play spells. I actually did not know it ended up as complex as it did. I didn't even know if the solution would work for the workshop when I first started it. As I analyzed each asymptotic bound in this entire simulate function, however, I found that they all originated from this play spells one, or all the big ones anyway. And that's complex enough in growth of time and space needs per extra card in hand that it overshadows the rest of the program. So that's going to be the focus of this workshop, is that play spells command. The preconditions of it. It expects a hand vector with integers, at least -1, because -1 would be lands, and then any other value above that is just the mana cost of the card. Since, though in the simulation, it's actually capped at 7 cards in your hand at any given time, plus, or at the end of a turn, because you can actually have 8 when you first draw for that turn. But this function can actually handle any size hand vector, so we can treat it that way as well. Damage per turn doesn't actually affect the runtime, but it's modified in this, so I figured I should include it as a parameter. And the size of other things, such as the deck itself, actually do not affect the runtime of this function. Several different combination vectors will be formed during the runtime of the function, and one will be selected as the final combination to be implemented that turn. Each combination is like the example earlier, where it could have chosen a 2 and a 3 or a 4, or any different combination that you can afford with the lands with the mana you can provide with the lands you have. The rest of the variables at the bottom are shown for the invariant loop method, which come later. And then after running, we will have the optimal card combination we played that turn. That's the part that we're looking at. So there are 3 different parts to the play spells function. The first part checks if there's a card that automatically uses up all the mana in hand, because that can save a lot of time. If not, the second part calls a recursive function called check card combo to find the optimal combination of cards in hand. More on that in a moment. The last one searches the hand for each chosen card and plays it. This is a closer look at that recursive function from the last slide, check card combo. It first checks if the current card in consideration is a land. If so, it ignores it. Then it checks if adding this card will cause the sum to go above the land count. If so, we bite off the branch here, because there's no point continuing because any other combinations that include this so far is already going to be not allowed. Finally, if there are more cards to consider, we make 2 new recursive calls, one where we add the next card in question to the current combination, and one where we don't. For each of these recursive calls, they end when they hit the end of the list, like the end of the last card in hand to consider, which, if it is still less than land count, is returned all the way to original call, where it is then compared with the other option, and the maximum of the 2 is taken, as long as it doesn't exceed land count, obviously. At the end, the combination that gives the highest total without exceeding land count is returned, so it can be played on that turn. These recursive calls look something like this, with green arrows being the ones that add the card, red arrows being the ones that remove the card in question. You might notice this is a binary tree. Worst case scenario, of course, assuming all the combinations could be played and that none of the nodes will be cut off for exceeding land count. Here's all play spells again. This time we're going to look at the nested for loops. Sorry. So at first, the for loops in play spells didn't strike me as any more than linearly complex. This table seems to show a simple multiplication pattern as the number of indexes for each increases. However, I realized the sizes of these for loops are dependent on the same factor, which is the size of the hand vector. So as one increases, the other is going to automatically increase, and therefore, when placed in a chart like this, we can see that the whole nested for loop has quadratically increasing time complexity as the hand size increases with sufficiently high land count, of course. Therefore, here are the asymptotic bounds for time complexity for the play spells function. Though in simulation is limited, on its own, it can have up to a linear, quadratic, and binary exponential time expectancy, all combined, the sum of all that. Or as low as a linear big omega times hand size if an exact match is found early. Therefore, big theta is theta h plus theta 2 to the L. The recursive function is going to be a constant theta plus both other recursive calls, or 2t times hand size minus 1 if, as it goes down to 0, cards left to consider plus that constant. At first, I thought it was going to be as simple as ordering the hand vector from highest to lowest mana cost and adding whatever could be added without going over the land count, just like from the bottom up. However, this would fail in situations such as where 5 lands were in play and the user had creatures of mana cost 2 and 3 and 4, because this method would just play the 4, and the most efficient use of that mana is to play the 2 and the 3. And actually, after solving this whole thing, I found this problem is one that occurs often in computer science, just in different forms. It's even in the textbook, and there it's called the subset sum problem. That one just returns a Boolean, true or false, of whether or not an exact match can be found, like an exact match of the sum. And this, the one that I have designed, is actually meant to find the closest matching combination without exceeding the maximum and returning that combination. Others exist online, but none of them were quite exactly what I needed for my program. For example, one of them searches for the closest sum, but allows the number to go above the indicated value as well as below, and allows repeated use of one item to reach the sum goal. So to clarify, the only new memory this function uses in all those combination vector, is all those combination vectors it makes for each recursive call. The rest of those variables and vectors on the left are parameters or global variables. However, even if we did consider them, even if we were doing the whole function of simulate, they would still be consumed by Greek letters incarnate because of the sheer amount of space needed for all these combination vectors that are produced by all these recursive calls. The for loop doesn't really affect memory that much, so unless you care about the integer values I and j that keep track of the index, so the space complexity will look a little different than the time complexity. The thing that does look similar, though, you'll see the space complexity turns out to be a binary base exponential in growth as hand size increases. Therefore, we find the following space complexity values. All right, I am running short on time, but here's my loop invariant method for check card combo, the recursive method. The loop invariant states that basically each iteration causes another 2 iterations that consider different combinations until the final one, and that each consideration is a subset of the hand vector, and each returned combination sums to be less than or equal to land count, and each are compared, and the greatest one without exceeding land count is returned. And also the loop invariant method for the nested for loops, which where a different pair of cards are compared at each iteration, and when a match is found, the next card and final combination is considered. Otherwise, the next card in hand is considered. Thank you so much. Here's the textbook, the game, and everything else used to create this Google Slides presentation. Thank you so much for your time, and have a good day.